Hey guys, welcome back. Glad to see you again. So, I wanted to talk a little bit about the lab that is scheduled for this week. So, technically speaking, there is no virtual lab. You have some review that's going to be done. The quiz is meant as a review of the materials that we've already covered in sort of early preparation for the test, which is a week from today on the 29th. But I want to talk a little bit about where you'll find this information, and that is in D2L. So let me show you D2L. Go awesome. So in D2L, what you'll see is that there's information from the lab manual that you'll be looking for. The other thing that we'll need to be aware of is that this lecture video is going to appear in the mixture separation lab information. And there's another video that appears here. How do we separate things seemingly inseparable? The lab that's done physically in the lab is to talk about how we separate materials. And the reason for that is because it's really only something that we can do in the laboratory. Now, while you aren't going to be expected to do that lab, you're not. There are some questions that you may see on the finals. Some of the lab finals have questions about this. And so we're going to talk a little bit about the lab, what it would entail, and some of the things that go with that. The reason that I do that, the real reason that I'm talking about this here, is because it goes to the nature of sort of what the lab is for and why we're in the lab. And one of the things I want to talk about, I hadn't opened this, I'm sorry, is that it deals with the scientific method. So part of what my job is to teach you about the scientific method. And I will post these slides to D2L when we get to that. So there's going to be some information about this particular lab that we're going to talk about. And then I'm going to talk about the scientific method in itself as part of what we're covering here. So what do we mean by scientific method? What the heck does that mean? Well, okay. The scientific method is a series of things that we do. So it's used in the laboratory. It's something we want you to keep in mind when approaching physical labs. You need to keep in mind as a virtual student because these things still apply. You're still being asked to learn about the scientific method, even though you're not physically in the lab. So this is how we develop these ideas and what they're meant to do. So we start with an observation or question. We research that to see, okay, what would I expect? You know, what are things that would make sense? This is usually, in this case, going through the lecture to talk about the materials that you might see here. So when we talked about elements and mixtures and compounds and how we might separate those things, that's the research that would go into this. We would then generate a hypothesis. So I have a thought that things might happen, okay? It's one of those things that might occur. And of course, the only way I know if that's going to occur or not is if I test it. So I have to test that hypothesis. And I have to design the experiment to try and do that. Once I've tested that and I've collected some data that goes with it, I have to analyze that data. Does that data actually say what I think it says, or does it tell me something else? Okay. And of course, then I report that. And of course, if it didn't tell me what I thought it was going to tell me, or if that didn't draw me to the conclusion that I thought it would, this might be something that we iterate. Okay. So all things begin with an idea. That idea is based on information that we've gotten or observed in the world. So something that we were told in the lecture. You form a hypothesis, an idea for that answer for that question to get an answer. So, for instance, here's a for instance for me. I can hypothesize that if I take a drink from my Cherry Coke Zero, I will be calmed down. It's a fairly common thing. I mean, you've probably seen me do it a billion times now. We've been through 5 lectures. I do it a lot. I have this idea because I have observed that I'm usually calmed down when I take a sip. It gives me a minute to pause and to breathe and to think. So there's a thought behind this process. I can then test that hypothesis by taking sips under various conditions. So I can try it when I'm already calm. I can try it when I'm frazzled. I can try it when I'm being stressed out by something going on around me. And of course, I can note my observations when those happen. Now, I can collect that data and I can look at all of that data and say, okay, does this tell me anything? So if I do it when I'm frazzled, do I end up being calm? If I do it when I'm stressed out, Do I end up being calm? If I do it when I'm calm, do I stay calm? These are the kinds of things that we want to do. And of course, a well-designed experiment will hopefully only change one thing at a time. So if we change multiple things, how do we know that the result that we're seeing is because of what we thought it was from? That's why we have to try and change one thing at a time. So based on the results of that data, I should be able to conclude if it is in fact the case in all scenarios which I tested. Now, am I ever going to be able to test every single scenario in the universe? No, that's really not a possibility. And that may be because there are scenarios that I haven't thought of, that haven't been considered. There may be variables that I can't control in things that we're doing. So all I can say from the data that I've collected is that either my hypothesis is still consistent, i.e. I haven't disproved it, or I can say, nope, I found that that was not actually the case. Okay, that's all I can do. There's no way that I can prove beyond the shadow of a doubt that that is always the case. There's no way for me to have done that. And so that's what you'll see is that the theories that we have become accepted because we have years and years and years of people trying to disprove them, and they haven't been disproven. Okay, we haven't found anything that's not consistent with that. When we do find something that's not consistent with that, we have to move. We have to change that theory to incorporate the new information. All right, so that's our scientific method. Now, this is important to you in terms of the laboratory because you have some knowledge that's been given to you through the lectures that we do. And so you should have, based on the knowledge of what we talk about in the lecture, what you've read in the lab manual, what you see in the virtual labs, that you can then take to say, okay, I expect it to behave this way. I expect it to do this. I expect it to do that. That should be something that you can do, okay? Given the scenario presented in the lab manual, you should be able to expect what you might see. Now, is it always going to work like that? No, absolutely not. And I'm going to tell you something. I really hope it doesn't, because we learn a lot more when it doesn't go the way we wanted it to, because then we have to figure out why. And that's really a better learning experience for us. Now, if it goes the way it's supposed to go, awesome, great. That's fabulous. I did it right. Yay. But it also doesn't give me any room to look at, what I did. All right. The lab is designed to test a hypothesis about the theories that you've been taught. So we're going to, you're always presented with collect some data. In the virtual labs, you're asked to collect some data. And then you analyze that data. You're asked to do calculations with it, or to theorize about it, or talk about it, or whatever. And then you're supposed to conclude that either your data does not support your hypothesis, and talk about why not, or that it's consistent with the hypothesis that was proposed. So if your data that you collected didn't match with what you thought it would be, there are a couple of reasons why that might be the case. Okay, and that's part of what we're going to talk about. So what is the test being done? What results did I expect? What data did I collect? Did anything happen that was not right? So did something happen when I was performing this experiment that wasn't what I was supposed to do? Did I make the solution wrong? Did I put something in the wrong place? Did I not heat it correctly? Did I do something that wasn't supposed to be done the way that was specified? Okay, and that's not a bad thing. That's not what I'm saying. What it means is that things were not controlled in the way that we expected. And so we have to be able to account for that. We have to be honest and say, this wasn't the way it was supposed to be. If I were to do this again, I would have to change that. Because I did it this way this time, the results might be different, and here's how. So it's important that we're critical of what we did, not only from the perspective of how could that change my results, but also in terms of how could that change things moving forward? What could I do differently to make that the results that I'm seeing more appropriate, more accurate, more what I was looking for? Okay. Now, all of these things can and do happen. All right. And that's something that you need to know when you're taking your data. Now, that again, in a virtual lab environment, this doesn't happen. Because if you do something that you're not supposed to do, it won't let you do it. That's just the way it works. But in a real lab, we would have things that would go not the way we expected them to. And some of those are in our control. Some of things, mistakes that we made, we didn't add the right thing, we didn't add it in the right way. Some of those are things that other people have done. Solution got contaminated. We didn't know about that. It therefore has affected our results. We may or may not be able to detect that. So these are things we have to be able to look critically at the information that we've collected to see, is there something that might be off? It's that smell test again. We need to know if it passes. So doing things wrong in the lab is not a bad thing. So many of the things that we have and use every day were discovered by such events. Penicillin is an excellent example of something that was discovered by accident. Champagne is something that was discovered by accident. These accidents can be really helpful to us. But of course, if somebody hadn't noticed that something was amiss and then said, oh, okay, here's this thing. What is this? What properties does it have? What does it do? How do I get to it again? Then we wouldn't have these things that we can now use. Okay. So it's important that you are clear and honest in your evaluation of what you have done. Okay. That is something that needs to be part of what you do. There is no judgment for that. There should never be any judgment. Oh, you did it wrong. That's not how this works. And I can tell you this from firsthand experience. My PhD, I didn't get any of the results that I expected to get, but I explored and explored and explored and explored and explored for 5 years to try and figure out why I wasn't seeing what I thought I was supposed to see. And while that's not a positive result, I discovered this, it is a positive result because I now know a bunch of things that it's not. And that's really useful information to the person who comes after me. Okay, so that is very important. So you need to be able to look at, okay, I didn't get what I wanted this time. What do I have to change next time to test this again? What else could I control? What else is important? What else do I need to look at? Okay. You never lose points. Never, ever lose points from me for doing something wrong. You never should. It's not what this is about. This is a learning experience for you, and it should be based on you learning from whatever you did, be it right or wrong. Okay. So if you did something that wasn't exactly right, then there'll be comments on that. If you lose points for not evaluating your work, like you get, like for instance, if you were in a physical lab and you were supposed to get a linear curve and it's not even near a linear curve and you make no comment on that, that's a problem. You need to have made some comment on why it didn't look the way it was supposed to look. Okay. For you guys who are online, you need to think about the lab itself and consider what might have gone wrong in the data collection. And that's what we're going to be talking about today. So that's why we're talking about this lab and why I wanted to talk about this part before we did that. Okay. So when we talk about the lab that would have been done if you were in the physical lab, in the lab manual, we'll see experiment 3, which is mixture separation. Okay. The objective here is to separate the components of a mixture in ways that we typically do in chemistry. And ways that we can do that is, if there are different solubilities, something will dissolve in water, something won't. We can use that as a way to separate them. Something will burn, something doesn't. We can do it that way. There are different ways that we can get these things separated. Usually that has to do with a physical change. Okay, so that's normally what we're trying to do, is get a physical change so we can get something to change phases and come somewhere else. If we're able to do that, that's good, because then we can get it back. If we have to combust it, we don't get it back. So, but that is kind of what we're talking about here. In this particular experiment, it's designed so that a 3-component mixture, ammonium chloride, sodium chloride, and silicon dioxide, will be separated into all 3 of those pure substances. The mass of each substance will be determined after we've done the separation, and then you can calculate the percent composition of that mixture based on each component. So once I know the mass of the ammonium chloride, I can divide that by the total mass that I had, multiply it by 100, and that gives me the percent that was ammonium chloride, similar to what we've done with our percent composition class. Now this separation scheme involves the sublimation of NH4Cl, ammonium chloride, which is a solid that sublimes. It changes directly from a solid to a gas. And so we set up this experiment so that we take and we heat this thing, and then the NH4Cl sublimes, and then we collect it on a cold piece of glass that's above it, and then we can take that cold piece of glass and measure that if we choose to. But we also know that the difference in mass between what I started with and what I have after I've done this is because of the loss of NH4Cl. So that weight difference is something that we need to be able to measure. So that's why we talk about how we do different weight measurements in the laboratory, because I'm now going to have an evaporating dish that had a bunch of stuff in it, and then I'm going to have the evaporating dish after the fact, and you have to take the difference between the two to get the mass of what's left, what has evaporated from that, okay, what has come off. Okay. We also have sodium chloride and silicon dioxide that are left after that sublimation. Sodium chloride is soluble in water. Silicon dioxide, sand, is not. So we can add some water to that, filter off the solid that's left, the sand that's left, dry that out and measure that. And then we can take the sodium chloride, drive off the water that's there, and then collect the solid from that. And the way we do that has to be done fairly carefully. And the details for how we do that are talked about in the lab manual. Now, there are steps in this procedure. It says to heat the beaker, and so we take a pre-mixed sample of the mixture. We weigh a clean, dry 100 or 150 milliliter beaker. We transfer the mixture into the beaker and reweigh it, so that now we know what the mass is for what I've added to it. We place the beaker and its contents on wire gauze supported by an iron ring. With a glass stirring rod, we're going to break stuff up just to make sure it's in smaller pieces. We heat the beaker and its contents over a gas burner. Begin heating near the top of the beaker and slowly move the flame down to the bottom. Heat with the hottest possible flame for 10 minutes. So the NH4Cl will sublime from the mixture and deposit on the cooler upper beaker sides rather than escaping up the hood if the sides of the beaker are not heated. So if I don't heat that beaker, the top part, then my sublimation will deposit onto those sides, and we want it to go away. So we need to make sure that that's heated before we do it. Okay. We allow the beaker to cool to room temperature, comfortable to the touch, weigh the beaker and the residue, and then we heat the beaker again and weigh it again. We want to make sure that that mass is constant, because if it's not constant, then we lost more material. So that's a problem. We need to make sure that that reaction is as complete as it can be. Because if we don't, and here's where this comes in, if I don't reweigh that and make sure that the mass hasn't changed, then I may have additional NH4Cl that's left over. That NH4Cl is soluble in water. So it's soluble in water, so it'll go with the sodium chloride. When I then dry the sodium chloride, I'll have additional mass in that stuff. And so the mass of the sodium chloride will be higher than it should be, and therefore we'll have errors in our measurements because of it. Okay? So this is a place that we can run into error. All right? And that's because of the way that we did the experiment. So we need to make sure that we've eliminated that error by making sure that that weight is constant before we complete that step. Now, after we do that step, then we're going to add some distilled water to the residue in the beaker to dissolve the NaCl. Okay, and like I said, if we hadn't gotten rid of all that NH4Cl, it would go into that solution as well. Now, we're going to stir that gently, make sure that everything gets broken up and then dissolved as it should. We'll then filter off the solid and leave the solution. Okay, we take that filter paper and dry that to make sure that all the excess water has left. Because if I don't dry it enough, when I take the measurement on the sand that's on the filter paper, and if it's still wet, then I have additional mass with that SiO2 that is not actually sand. And so we get an error in that mass because of the presence of the excess water. Okay. After we've done that, we can take that sodium chloride, put that into an evaporating dish, carefully evaporate it. And you'll see that there are steps that are talked about in here to make sure that you do that carefully, because if you do it too fast, then the water that's in there boils and the solid goes flying and you lose it. And so you have a loss in material because it went out of the beaker, and that's a problem. So we have another place for error that comes in there if we heat it too fast. Okay, so there is that too. We also have to make sure that that NaCl is as dry as possible, because again, if there's additional water in it that shouldn't be there, then the mass will be higher than it should have been. Okay, so those are the places that we can run into errors because of how we've handled this data. Now, why am I busting your head about all of these places that these errors can occur? Okay. Because that's probably the kind of question you're going to see when we talk about this on the final. So you may see that it says that after this step, the mass is more than it should be. After this step, the mass is more than it should be. You'll be asked, why? How do you know that's an error? Why did this happen? What could possibly be causing that? Presence of water could be causing that. Could be that we lost material. There are lots of different things that could happen here. And it's an analysis of what you've done and the errors that can occur because of it that you need to be looking at when we do this discussion of what might have gone. Okay, so that's where we are with that. Now, questions, comments, problems on any of that? I hope not. Now, in addition to what we're talking about in terms of that mixture separation, in ALEKS, what you'll see is that there is a post-lab for reactions. And this post-lab is a quiz that includes things like balancing chemical equations and matter and units of measure and all the stuff that we've talked about so far. So that is in my assignments. Someday it will be done loading. Hooray! So post lab for the density. Nope, that's not the right one. Post lab. Oh, that's right. Hasn't shown up yet. Post lab chemical reactions. This is the quiz that is supposed to go with the lab. All right, I opened it today, but it's technically supposed to be done tomorrow. This is the quiz that goes with that. So this will go through things like balancing chemical equations, all of the stuff that we've talked about so far. Now, in terms of what you can do to prepare for that, these are the same things that you can do to help you get ready for the first test. Things that I have provided that are useful to you, in addition to ALEKS, because you'll have to finish the ALEKS, and if you don't finish the ALEKS, there are penalties for that. Points taken off if it's not turned in when it's supposed to be. In each of these lectures, there is practice. These practices simulate the kinds of questions that I would ask you on a test. There is also in-class practice sheets. Now, these in-class practice sheets are not direct representations of what I would ask you, but they are meant to help you practice, to sort of beat into your head these different things that we've talked about. Okay, so how do I do these calculations? How do I convert these things? How do I, how many protons, neutrons, electrons are there? All of these things are meant to be repetitious practice of the ideas that we've talked about. So if you need more help, this is where I would go. Start with these, build your way up, okay? And of course, this one is really long, and that's why I'm opening it for you. This is really long for a reason. Now, I didn't intend for this whole thing to be here. I meant for part of this to be here, because I thought the discussion that was here was informative about some of these things. I didn't really expect the whole thing to come in, and I haven't been able to get this modified so that it doesn't do that. Now, this particular textbook, Introduction to Chemistry, this is the parts that I thought would be useful, and measuring matter, dimensional analysis. Those are the things that I meant for lecture 1. Now, if you scroll way past this, down here to 460, here are some actual practice sheets for this material, okay? Now, that book is great. I think it's really nice, but I did not intend for all of that to be there, and I apologize that I haven't been able to cut it down a little bit, but I am not able to do that with that document, so sorry. So these are practice for this one. Let's see the atomic structure. Here's some practice for that. Names and formulas, practice for this. Okay, and like I said, it is highly repetitive. It is, it really is. It's meant to be that way. And this is only if you don't know how, so if you don't know how to do the ALEKS, if you don't know how to do the other questions I've asked you, come here, try these. And I'm more than happy to sit with you and walk you through all of this, because I haven't provided answer keys for these. So I'm more than happy to sit with you and walk through all of this. That's what they pay me for, so don't worry about it. But there are sheets for all of the stuff that's on the first test. On the first test is lectures 1 through 6. We will do lecture 7 before the test and review on Monday. The test is on Wednesday. Okay. there is also exam 1 practice, and there are answers for this. These are questions that are samples of what I may ask you on the test. I will tell you, and I mean this in no kidding term, this is actually true. I often take my test questions directly from what is here. No changes, no whatever. So that you've seen that practice. Now it may be that I've changed some numbers in a slightly different calculation, that kind of thing. But this is, this is meant to be practice for you guys for the test so that you can see what kinds of things I'm going to ask you to do. Okay. So this is a very excellent way for you to practice. All right. And this isn't meant to be too. There is an answer key that goes with all of this. So, and it's handwritten, so I know it's a little bit messy, but I will be happy to answer any questions about that you have that those answers don't address. Okay. So there is that. Like I said, I will be going over parts of that on Monday if you have questions, and you can talk to me about anything between now and the day of the test. I will be in WebEx when the test is going on. The test opens at 8 a.m. It closes at 10 a.m. It is a 2-hour test. So if I understand it correctly, you can get in until 10 a.m. So you can take it up until then, kind of deal. But there is that. So I think that's everything that I had to talk about in terms of lecture, lab, that kind of stuff. Now, as far as practice for chemical reactions, practice for that. There is balancing equations, and there's a bunch of them here. So there's 5 pages of balancing chemical equations. And this includes both nuclear and non-nuclear. And then there is the practice in the chemical reactions. So there is practice here as well. And then there is another worksheet that's here. So I have an additional one for this. So lots of practice that goes with that. And anything that you have questions about that you can't figure out, please go ahead and ask me. Okay. So that's everything I have for you at this point. I'm going to go ahead and stop this now. And I will talk to you guys soon. See you on Friday.